Hello. So, in this video we are going to be covering geometric versus analytic reasoning. And we're going to sort of cover this sort of separately in this video because there's a lot of generally confusion about sort of what the differences are and whether or not you want to sort of use one versus the other. So, the goal of this video is really to sort of clarify what we mean when we say these things and sort of why we care about these things. That's the hope. That's the dream, all right? So, geometric versus analytic reasoning. So, over time, sort of historically speaking, things have been largely relegated to analytic reasoning, and there's a lot of reasons for this that sort of may or may not have sort of valid, relevant use to today. But the long and short of it tends to be that it's very easy to talk about sort of numbers instead of trying to know what somebody is thinking. And so the sort of analytic part of it is much easier to sort of see if somebody is doing it right versus the geometric part, which is sort of much more abstract typically. Okay. But the downside of this is that it sort of gives this false impression that this analytic methods or this analytic point of view is the sort of better way to do things, and that geometric stuff is sort of for people that aren't good enough for the analytic or something like that. And that is just very untrue. And in reality, actually, even research-tier mathematicians, like people that are doing cutting-edge research in mathematics, they almost all of them use geometric reasoning as a starting point to understand what they're trying to deal with. And then once they sort of have a good intuition about it, they try to then use the analytic tools to explain it to other people, okay? Because again, it's sort of easier to write down numbers and equations and things and be very precise with what you're trying to say rather than being like, well, picture, a cloud that has like sort of a glass structure but like has really smooth corner, like this is not a thing that you can really explain very well and have it sort of make sense to somebody, right? So the analytic thing is how we sort of explain something, but the geometric side tends to be how we first sort of understand it in the first place, okay? So this geometric reasoning piece is really just as useful as the analytic reasoning. It's just that they have sort of different roles. They're different parts of the process, okay? So starting with geometric reasoning. So one of the sort of important things to state right off the bat is what geometric reasoning sort of isn't. So a lot of the times, like a lot of memes and things you'll see, when you see somebody picturing math, it's like they're staring off into space and all these like equations are drifting along the page and stuff. That's not what that is. People, like mathematicians, don't visualize equations. That's sort of, there's no value to that because you could just write it down and look at it instead of picturing it, okay? So instead, what they're looking for is structure, patterns, relations, sort of pattern recognition. They're looking at sort of examples of what they're thinking about and trying to visualize why stuff works, how stuff changes over time, that kind of thing. And the sort of go-to version of this is graphing. So graphing is sort of the classic geometric tool, but it's not the only geometric tool, right? A lot of the times these things become sort of almost analogous in a person's thought process, that they're like, when you say geometric reasoning, you mean graphs. But it doesn't have to be that. So it could be other things too, like drawing a picture to represent a word problem, or even drawing sort of abstract things. You could draw, arrows or like little squiggles. And as we see in other sort of videos, we have like, potato diagrams or cloud diagrams, and these are geometric reasonings. This is the way of understanding what we're trying to talk about by visualizing it instead of just writing down some letters and numbers, right? So by way of example, when we talk about like vending machines and trying to understand how functions work, the vending machine picture, that's an example of geometric reasoning, right? Even though it has numbers and letters, that's not the point. The point is literally visualizing the system that you're trying to represent, okay? So geometric reasoning, the pro, right, the good parts of it, it's good for big picture information. It's good for understanding how the different pieces sort of fit together, right? This structure, patterns, and relations bit. It's good for getting a bird's eye view of what you're trying to accomplish and how things are sort of interrelating that you're trying to sort of tackle. The downside is that it's not usually very good for precision, right? It might tell you that like there is a maximum or minimum somewhere because that's how the structure has to change, but actually finding it is not something geometric reasoning would be terribly useful for, okay? So then we get the other side of this, right? The analytic reasoning. And again, these aren't competing viewpoints. They're sort of two sides to the same coin. You use the geometric part as sort of a starting point to understand what you're trying to do. And then the analytic side is where you can dig in and actually get sort of very nitty-gritty pieces. So analytic reasoning then, the very strength of it is almost the opposite of the geometric part, where you abstract away from that context. You move away from the pictures into something that is very sort of cut and dry that you can manipulate. So the classic example, algebra, right? As you sort of move from here's a picture, I'm going to assign sort of variables and numbers and equations to this picture and build an algebra sort of setting, right? Build some equations that represent my idea. Once you get that on paper, then you can actually do things to it where you don't actually have to worry about what that means in the picture as much, right? And so this is helpful as a way of doing logical deduction, right? Once you've sort of abstracted out and you have like an equation, for example, there are rules that you can use to actually manipulate that thing, right? Like adding numbers to both sides or dividing both sides by a number or moving an unknown from one side of the equality to another to isolate something. This is something that's hard to do with a picture, but is much easier to do once you have it written out as an algebraic line, right? And in that same vein, you can use identities. You can use that, like, if this thing equals that thing, I can interchange them in my algebra, right, in my equation, and get some sort of step in the right direction and eventually an answer. So the strength then of analytic reasoning is that it's precise, right? It can actually get you the values. It can tell you the time value that you're looking for is like 3.7862 seconds, which is not a thing you would ever get from sort of picturing the system. But what you were even looking for in the first place is probably something you got from the geometric side. And that's because analytic reasoning, one of the sort of downsides, is that there's not really much or any big picture or contextual sort of background sort of inherent to the analytic reasoning. There's always sort of this big picture context floating in the background, but that was the geometric part of it, right? So once you're sort of doing the algebra manipulation, it sort of isn't clear what that context is anymore. And so that's sort of the weakness of analytic reasoning, okay? So by way of sort of a silly but, surprisingly apt example, what if you're building Legos? Who doesn't love Legos? Monsters, that's who, but regardless. So the geometric example here, like in this Lego kit instruction guide, the picture here gives context, right? So the pictures, like 1, 2, 3, 4, whatever, these pieces, these are sort of the graphical reasoning. And at some level, like most of this works just fine when you're trying to do the sort of big picture pieces of it, right? Like when you're looking at the step of 1 to 2 to 3, there's sort of small enough going on, and the picture is sort of big enough in the literal sense that you can sort of see exactly what you need to do. But sometimes there are times where you need like a blown up version of it, right? Like in this corner where it's sort of like a sub piece that involves sort of very carefully sort of getting stuff together and sort of pre-building it before you can sort of insert it into place. And this is sort of the analog to the analytic piece of it. It's trying to explain those little details in sort of much more sort of piece by piece steps instead of just sort of giving you a picture and hoping you can sort of figure it out from there, okay? All right, so what do? We talked about analytic and geometric reasoning and how a lot of the times these are viewed as sort of pitted against each other, like one is better than the other, or problem by problem, you want to use one or the other. But the reality is that these things are complementary ways of looking at something. Really, for every problem, ideally, you want to use both of these methods. You want to start almost always with geometric reasoning to get a sort of big picture idea of what's going on with your problem, and then come in with the analytic tools later when you've figured out what it is you're trying to get, what it is you're trying to do, so that you can bring sort of the precision of math to bear to get an answer that ends up being accurate and precise. And that's not necessarily something you can always do with the geometric side. So both of them sort of are useful in their own spheres on any given problem. Okay? So that is that.